Okay, this is the second hour of Physics 1C for September 1st. We just got done talking about pressure and got the recording going. I'm pretty sure I got the recording going. Yep, it's going. So, all right. Next thing we're going to be talking about is how pressure changes the deeper that you go into a fluid. So we call this the variation or the change of pressure with depth. So the idea that we would like to explain here is, why is it that when you swim to the bottom of a pool, or you swim deep in the ocean, or you swim deep in a lake, why is it that you start to feel a lot of pressure on your ears? That's what we want to kind of answer right here. And then we'd like to go a step further and say, well, I know that I feel more pressure, but how much more pressure? We'd like to be able to measure how much pressure do I feel when I go like 1 meter deep in a pool, 2 meters deep, 3 meters deep, and so forth, right? Turns out it's a pretty easy calculation, but just like all things in physics, when we can derive something, we try to derive it. So we'll start off with this. Let's say that we have a container of water. Let's make the container a different color. And let's erase the top of it again. So we have a container. We're going to fill this container with water, although it does not have to be water. This would work for any fluid. So we fill this entire container up with water. Now, we're going to behave as if the water itself is still, okay? So it's not flowing really in any way. So the water is kind of still. Just say it's still, okay? Now, that doesn't mean that there's not little molecules that are zipping all around here. There are. But in general, we're going to say that the water is still. And what we're going to do is we're going to analyze the forces that act on a column of water within this fluid. So we're going to look at a column of water. Scoot this down just a little bit here. And so I'm going to draw a little column of water in here. And what this is going to be is we're just kind of looking at the forces that act on the water itself, okay? So I'm not drawing an object in here. What I'm drawing is a column of water. Whoops, that is a little bit too big. Just be a little more careful with the way I erase it. Like that, and like that. Okay. So here's our column of water. Okay, and I'm going to tell you that it has dimensions, so that on the total height of the column of water is going to be h on this side. It's a cylinder. And the area on the ends is going to be a. So this area is a, and there's also going to be an area down here as well that we'll call a. Okay? And again, this isn't an object that I'm placing into the water. This is like... it's like just looking at a piece, imagining what a column of water is and the forces that it feels. Does that make any sense to you all? Hopefully it will as we do this. I always found this to be a really confusing way to do this. But, like a chunk of a puzzle? Yeah, something like that. Yeah. Your book has its own way of doing this derivation. I don't think it's very clear. I'm not going to say this is the most clear, but stick with me. Hopefully it'll make some kind of sense to you. But again, the idea is we've got some water, and now we're just imagining that we kind of draw out a line of a cylinder of that water, and we're going to think about what are the forces that are acting on this cylinder, okay? And I'll start off by saying, well, any object that's on the surface of the Earth has a weight, right? Everybody would agree with that? This column of water has to have some weight to it. Obviously, it's a column, it has a volume, so it has a mass, so therefore it has a weight, right? And I'll use a vector to draw that force on here, and we'll just say, okay, that's one of the forces that would be acting on this column of water. It's going to have a weight. Now our idea here is that the water is still, and that means that our column of water that we've chosen out of this object, it is also still. It's not moving. It is in equilibrium. It's just sitting still, right? And that means there have to be some other forces that balance this weight out. After all, if there was no other force to balance this weight out, what would that column of water do? Without another force to balance out the weight, it would move down, right? That would mean that this column of water would have to sink to the bottom, right? Now, of course, it would sink, and then it would hit the bottom, and maybe it would just, splash out. I don't know. But then, if that was all, think about this. If that was all that was going on, wouldn't all the water in this tank just always be moving downwards? And that'd be kind of weird, because it's sitting still, so it's not moving downwards. So there must be some other forces. So what could those forces possibly be? Well, we learned about this idea just a second ago, which is pressure, right? We know that there's this thing called water pressure, and it exists within this fluid. And if I had put like a piece of paper in here, if I put my hand inside of this water, stick my hand in the water, and I would feel pressure on all sides. So certainly, the water must exert pressure kind of on itself in a way. So there should be water pressure acting on this surface, okay? And that means that there's going to be a force that's going to act on the top and bottom due to the water pressure. There's going to be a force acting from down here. Oops. There's going to be a force that's acting on the bottom. And there's going to be a force that's acting on the top. Now, there will also be forces acting on the sides, okay? But let's just talk about these two for now, okay? I'm going to call the force on the top F1. I'm going to call the force on the bottom F2. And again, I'm saying that these forces are coming from pressure. So remember what we just said a second ago, which is that pressure is equal to force divided by area, right? So we can also remember we can rearrange this to say pressure times area is equal to force. So then what I'm going to say is that the force F1 is going to be equal to whatever the pressure is at this point right here, so we'll call it P1, multiplied by the area of that the top of the cylinder. And the force on the bottom is going to be multiplied by pressure 2, multiplied by the area. Okay, now you might ask, well, how do I know that the pressure at the top is different from the pressure at the bottom? And I could say we don't really know that that's true, except for kind of our experience tells us that it's true. At the very least, our experience tells us that the pressure up here at the top of the fluid is not as big as the pressure at the bottom. That's what our experience tells us. So there's no reason to assume that the pressure at the top is the same as the pressure at the bottom. We might as well make the assumption that they're different. Maybe that assumption's wrong, but yeah. The height will come into play, Troy. Don't worry about it. We'll get there. Yeah. But look, that's what our goal is, right? The goal of this whole thing is to find the variation of pressure with depth. That is to say, how does the pressure vary when you go different depths within the water, right? So that is right. We'll use the height for finding the differences. But our goal is to find our real goal is to see what the relationship between pressure 2 and pressure 1 is. That's our goal here, right? What's the relationship between these two different pressures right here? I'll write that at the top here. What's the relationship between the pressure at the bottom, P2, and the pressure at the top, P1? That's our question here. That's what we'd like to answer. Okay, does anyone have any questions before I keep going? The next few parts of this, I think you all will be pretty comfortable with. Like the next few steps that I do, you'll be like, oh yeah, I remember all that stuff. The real question is, do you understand the setup? of what we're about to do, because if there's something you don't understand about what we're trying to do here, then now would be a good time to ask. We've got a column of water. All of the water in the container is still. We're looking at the forces acting on that column of water. We acknowledge there must be a weight. There must be some pressure on the top. There must be some pressure on the bottom, right? And if the entire container is still, well then, that means it's in equilibrium. And what do you all remember about equilibrium in Physics 1A? When a system is in equilibrium, what do we know about it? There's two things that we know. The sum of forces is equal to 0. That's exactly right. That means that if I sum up all the forces that are acting on my column of water, they should add to 0. Now, we're not looking at the forces on the container. We're looking at the forces just on a column of water within the container. And it really is just an imaginary column of water that we've drawn out right here. But it's useful. So, if the forces sum to 0, we have two forces pointing down and one force pointing up. So the way that I would write that is F2 minus F1 minus W is equal to 0. Would everyone agree with that? Does that seem reasonable? Looks about right? Okay. Now, again, we said that the force coming from the bottom is coming from the water pressure. There's water in here. It exerts pressure on all surfaces. It must exert a pressure on the bottom. That pressure was whatever the pressure down here is. This is P2 is the pressure at this point, right? So P2 times the area, that gives us the force on the bottom. So we plug that in here. F1 is P1 times A, same area, because we chose to make a cylinder that has the same area on the top and the bottom. And that's going to be equal to the weight. Now, weight is what? It's mg, right? Let's go ahead and plug that in for the weight. Where now m is going to be the mass of our column of water. All right. So let's start putting some other things in here. I would like to get rid of this area. Okay? So what I would like to have happen is I would like for the area to show up on the right-hand side of this equation. Take a moment and think. How could we possibly do that? How could we get the area to show up on the right-hand side of the equation? Two pi r times h. What is 2 pi r times h? That looks familiar. 2 pi r sounds like the circumference of a circle. If you multiply that times the height, I think that's going to give you the surface area of the curved portion of the cylinder. I don't think that's going to help us in this particular case, Troy, but you're on the right track. Robert has the right idea, but I need more details. What does that mean? Density times A times H. How do I use it? Now remember, go back to the original question. The goal is, okay, the goal is this. I want to get the area to cancel out of my equation, which means I need the area to show up on the right-hand side of the equation. You want to replace m with those variables. Well, how do we know we can do that? So what was mass? What did we say mass was earlier in terms of density? Let's start from there. Yeah, you're exactly right, Robert. Robert's got it exactly right. He's got all the details right. Mass was density times volume, right? Okay, well, let's plug that in. Mass is density times volume times gravity. P2 minus P1. You guys okay if I factor out an A right here? They both have A in it. We can factor it out. Okay, yeah. Density times volume times gravity. What's volume in this case? Well, let's go look at our picture. How can I describe the volume of this object? The volume of this object right here, what would it be? That's right, the volume of the cylinder is equal to the area of the top multiplied by the height. Exactly. Does that make sense to everybody? The area times the height is the volume, because you just take the area of the top and you multiply by how big this is. That's how you get the volume of the cylinder. And just to kind of correct Troy where you were coming from, the way that would be written normally, what's the area of a circle? Pi times what? Area of a circle? I know you all know this. Maybe you're all just reluctant to type it. What's the area of a circle? How do you calculate it? Pi r squared. There you go. Yeah, pi. This would be the volume of a cylinder in general would be pi r squared h. So you were saying 2 pi r h, Troy. It would be pi r squared, right? Just to kind of like follow that back up. Okay. So we don't need this though because we didn't even put the radius into our equation, right? We will use it for another. Okay, so we know what the volume is, and we said, just to recap what we're doing, systems in equilibrium, we're summing forces. That means we take F2, which goes positive, that's why it's positive, up, minus F1 minus W. We replace F2 with P2 times A, pressure times area is force. F1 with P1 times A. We move the weight to the right-hand side, which I replaced with mg. We are now going to replace the mass using the equation that mass is equal to density times volume. Very useful in this class. To remember this one. Very helpful. And the final thing we will do is we will replace the volume with the area of the end cap times h. And that kind of brings us to the end here, because now we'll have P2 minus P1 multiplied by the area is equal to density times area times height times g. And now we have an area on both sides that we can cancel out. And we get our final results, or one version of this, I would say. Which says that the pressure at the bottom minus the pressure at the top is equal to density multiplied by gravity multiplied by the height of the column itself. And this is effectively the equation that we have for the variation of pressure with depth. And if you think about it, it's a very simple relationship. It says that the pressure 2 is bigger than pressure 1 by this amount. Right? That's what it says. Pressure 2 is bigger than pressure 1 by the density of the substance, in this case water, times gravity, times however deep you are in the fluid. This assumes the area on top and the bottom are the same. Yeah, the trapezoid won't work. Well, you have to understand, Troy, that we were free to make this shape however we wanted to, right? And the result that we got has nothing to do with the shape. You notice that? The shape doesn't matter anymore. The result is just true. Yeah, the area is not there anymore. So, could we have done this in a way that we made our shape different? Maybe. We would have gotten the same result, certainly. It just would have been more complicated. So, I mean, to say that a trapezoid won't work, Troy, I probably would just be a little more tricky. Probably just be a little trickier, but we'd probably still get to the same result. Because this in general is true. Now, we usually write this in a little bit more useful way, and the way we do that is this. So, there's going to be two other forms of this that I'm going to write down here for you to help you out with understanding these things. So let's say we take the same situation, okay? And instead of making pressure 1 at some point that's somewhere in the fluid, what if we just make the top be P1, and then we come down to some point right here, which is a distance h down here, right? And we use that for P2. Okay. And in fact, let's change our notation here, okay? So I'm going to call the pressure down here just P. And I'm going to call the pressure on the top surface, I'm going to call that P naught. Okay? And I'm just going to tell you right now that P naught is going to represent atmospheric pressure. right? Because there's a pressure that's exerted on the outside here from the air, right? Up here you have air pressure. And that air pressure pushes down on the top of the fluid, right? And it exerts a force. And the amount of pressure that's there is, 1 atmosphere of pressure. Or, as we saw earlier, that's about 1 times 10 to the 5 pascals, approximately. 100,000 pascals, right? So, if we replace P2 with P, and we replace P1 with P naught, then we get, I think, an even simpler relationship that says that the pressure at some depth in the fluid is equal to the pressure that's pushing down on the surface of the fluid. No, I didn't quite finish the... Here, let me rearrange it. The pressure at any depth in a fluid is equal to the pressure on top of the fluid plus rho times g times h. There we go. This is usually the way that it's written. And this is our equation for the variation of the pressure with depth. Okay. We'll do a little quick example here. Something simple to describe this, and then we'll do something a little more complicated, but does this make sense? It says the deeper you go, the more the pressure increases. And the amount of pressure is going to increase based on how big h is, how fast gravity accelerates at your location. This should just be 9.8, right? And it depends on the density of the fluid, right? So if the fluid is more dense, the pressure increases a little bit faster, and the farther down you go, the bigger the pressure is. Yes, that's right. The units of h should be in meters, g should just be 9.8 meters per second squared, and then density, this is where you want to measure your density in, 1,000 kilograms per meter cubed. Okay. Right. That's right, Wynn. So if we choose the top point to be the surface of the fluid, the water surface, then you use the atmospheric pressure. Precisely, yeah. And again, you're going to see this symbol be used throughout your homework and in the textbook and in examples. I'll use this. This is always atmospheric pressure, okay? P naught, atmospheric pressure, okay? All right. So let's ask the following question. Let me just type it because I feel like I can type it a little faster. I know you guys can't see this. I will make it bigger. Why are none of the options to make it bigger? I have to do this, and then I have to do this, I guess. Okay, there's the question. How deep do you have to go in a body of water to feel a pressure that is double atmospheric pressure? Does the question make sense? How deep do you have to go in a body of water to feel a pressure that is double atmospheric pressure? Does that question make sense? Can you all try to figure it out before I do it? Can you all take a minute? Try to work on it? Take a break from me talking. Let you guys work. Yeah, you don't need to drive this again, Donald, no. You can just use this equation. Okay, hold off on the answer, Mustafa. It's good that you got an answer. I was gonna... That's okay, though. So Mustafa got 10.3 meters. That is the right answer, by the way. But everyone else, just keep working. Don't worry about you get it right or wrong. Just try to figure it out yourself. Okay, I don't know if that was enough time, but we're going to go ahead and go through this. And when we do, like, there's going to be other times when I give you more time, but this is a shorter problem. So if you weren't able to completely solve it, that's okay. I'll give you more time whenever we're doing kind of more serious problems. This is just kind of a way. The whole point of this question is to get a feel for how this equation works. That's the idea. Looks like a lot of people got answers too, so that's really good. And again, if you didn't get the answer yet, that's fine. We're here to learn, and you know, if you don't instantly pick up on things, that's just how it's going to be. It's hard to know the answer and know how to use the stuff the first time you see it, right? So, but making the attempt goes a long way to helping you to understand things. That's all that matters. Okay. So, by the way, so we're using 101, 300,000. I mean, either one that you use, you're going to get pretty much the same answer, Troy. You know what I mean? It's going to be pretty close. Yeah. And I mean, 10.2 and 10.3, they're basically the same answer, right? Especially when we're not doing a calculation that's going to support astronauts going to Mars, right? We're doing just kind of a rough back-of-the-envelope calculation to get an idea of these things, right? All right, so what do we know? We're given a pressure of double atmospheric pressure, so that's 2 atmospheres. One way you could write this is you could write it as 2 times P naught if you want to. But we're just going to say it's 2 times 10 to the 5th pascals. And I guess it probably helps to draw a picture here. So, well, this is basically our picture. Yeah, this is the same picture, isn't it? I don't need to draw a new picture. You can delete this. The pressure at this point at some depth h is 2 times 10 to the 5th. The pressure at the top, P naught, is 1 times 10 to the 5th. And what else do we know? Well, we know the density of water. The density of water is 1,000 kg per meter cubed. Here, just to kind of distinguish what we're doing from the work we had done before, let's make this a different color. And finally, we know one other thing. We know G. G is 9.8 meters per second squared. And our goal here is to solve for h. Now, what I would like for you to do when you solve problems like this, if you can, you won't always be able to do this, we want to solve for that variable, right? So let's isolate it. So let's take P naught and move it to the left-hand side. And let's divide by rho g, so we get P minus P naught divided by rho times g is equal to h. And then we plug all our numbers in, right? So since you all have already done this, I guess I can write it all in here. So it's P, so it's 2 times 10 to the 5 pascals minus 1 times 10 to the 5 pascals. And then we divide all of this by rho times g, so that's going to be 1,000. Rho, density of water is 1,000, times g, 9.8. And this gives us about 10.3 meters, right? I guess if you do it this way, maybe you get 10.2 meters. I'm gonna just round it down even worse, because the whole point of this was just to get a rough idea. We're gonna call it 10 meters, okay? So that means for every 10 meters that you go beneath the surface, yeah, exactly, Troy. What I'm doing, the simplest way to put it is when you see me solve something in class, that's basically how I expect you to solve it on an exam or on your homework, like your written homework. So yeah, this is the rule. I mean, it's not that complicated. The idea is you write down all of the known variables, you write down the equation that you're using, you solve the equation for the variable that you want, and then you plug everything at the end. That's it. That's what I want you guys to do. And in this class, you can do that with pretty much most of the problems. Yeah, it's not just physics classes at this school. It's physics classes everywhere. This is how you want to get used to doing this kind of stuff. Okay, does anyone have any questions? That's pretty simple, right? It's just a basic usage of this equation, and you know, it turns out that every 10 meters you go, you get another atmosphere of pressure, right? So if you go to 20 meters, what would the atmospheric pressure be if I go to 20 meters? 3 atmospheres, right? Exactly. And if I go to 30, it's going to be 4 atmospheres. If I go to 40, it's going to be 5 atmospheres, right? And it starts to get really, really high pressure really fast. Okay. Okay. Now, there's a couple other things I want to say before we do another problem here. That is, let us go back to, I think it's this equation. Let's say a couple things about this. So let's grab this picture here. Let's repaste it down here. And I'm going to say a couple things about this equation. Let me move this here, move this here. All right. So there's another way we can write this that uses derivatives that we're going to need, okay? And in order to write it in that way, we are going to have to come up with a couple other lines that we're going to draw on here. So I'm going to draw those lines. So we're going to draw a line from down here to down here, and we're going to call this one y1. And then we're going to draw a line from here to here. We're going to call this one y2. So y is a variable measured in the positive y direction, just like we normally would. You know, positive y is up in this case. And we're saying y2 is the distance from the bottom of the container to the bottom of the surface. Y1 is the distance to the top of the surface. Okay. And then what we can do is we can kind of rewrite our equation in the following way. P2 minus P1 is going to be equal to rho times g. So now what would h be? Well, h would be y1 minus y2. Okay. And I'm going to write this a little bit differently. I'm going to write it as P2 minus P1. And then what I'm going to do is I'm going to factor a negative sign out of here. So we can write it like this, negative rho g. Now it's going to be y2 minus y1. Sometimes when I do this operation, or this algebraic step, some people get confused. So these two things mean the same thing, right? Everyone agree? If you don't understand, multiply the negative sign through here. You'll get negative y2, and you'll get negative negative positive y1. So these things mean the same thing. So you reverse the order by factoring the negative sign out. Now, why did I do that? Well, because I noticed that when I write P2 minus P1, and I write y2 minus y1, notice that P2 is the pressure at the bottom, y2 is the height at the bottom. P1 is the pressure at the top, y1 height at the top. So when I do like 2 minus 1 on this side and 2 minus 1 on this side, this is really commonly written when we're in algebra. Yeah, it looks like slope. That's exactly right, Troy. That's exactly right. It looks like slope. And how do you write slope? Well, you can write it like you wrote it, or you can write delta y over delta x, right? So what I'm going to write is, on the left-hand side here, we're going to write this as delta p, the change in pressure. On the right-hand side, I'm going to write delta y. Is everyone okay with that? Delta, of course, means you take the difference between the pressures at 2 points in the fluid, in general. Now I'm going to rearrange this, and I'm going to move the delta y to the left-hand side, and I'm going to put the negative sign over here too. And then the final thing that we're going to do, something we do pretty commonly in these classes, is we're going to take a limit as delta y goes to 0 of this whole thing, which is going to make it so that the expression, if I let delta y go to 0, then delta p over delta y is going to become a derivative. So we're going to get negative dp dy is equal to rho g. This is another expression of variation of pressure with depth that we're going to be able to use in certain problems where we have to use calculus. I mean, this is a calculus expression. What this tells us is the rate at which pressure changes with respect to depth, right? That's what a derivative is. dp dy means the rate at which pressure changes with respect to depth is a constant. That's what this says, right? It's a constant. It's equal to the density of the fluid multiplied by g, assuming that the density of the fluid is constant. The density of the fluid may not be constant, but in a lot of the problems we do in this class, it will be. Okay. Anyway, point is that dp dy is equal to rho times g. The rate at which pressure changes as you go deeper is equal to this constant right here. So this is another expression of variation of pressure with depth that we're going to use when we do problems where there are like dams that are holding up lots of water, but the dam is, we got to figure out how much pressure is there on the dam, and we'll have to use this to help us with variation of pressure with depth. Okay, and what was the other way I wanted to write this equation? No, I think that's it. That's all we need. Okay, so this is going to come up a little later. We'll start off by doing problems where we don't use this, and then as we get into more difficult things, we'll have to use this. Does anyone have any questions about that? Boy, does the time go fast. We are on... I kind of want to do this problem, and then we'll come back and talk about Pascal's principle afterwards. Let's make this a little bigger so you all can see it. How well can you all read this? I know everyone's reading on different screens. Let me know how much bigger I need to make it to where you can actually read the words. Do I need to go bigger? We can go bigger. Like that, maybe? Is that big enough?
That's good.
All right. The lettering is a little bit... yeah. So, here's what we want to do. We want to estimate the force exerted on your eardrum due to the water when you are swimming at the bottom of a pool that is 5 meters deep. Okay? So you're sitting at the bottom of a pool that is 5 meters deep, so 5 meters right here. And here's the surface of the water. And you are lying down here at the bottom of the pool, or you're swimming somehow at the bottom of the pool. And here's your ear. And we want to figure out the force exerted on your eardrum due to the water when you're at the bottom of a pool that's 5 meters deep. We're going to go ahead and call 5 meters equal to h. I'm going to go ahead and put the equation you need right here. You will need the following two equations to solve this problem. And let's read the bottom part right here. It says, this is something that's, I think is very interesting. It says, the air inside the middle ear is normally at atmospheric pressure. So that's saying the air inside of your ear canal, right, is normally atmospheric pressure. Therefore, to find the net force on the eardrum, we have to consider the difference between the total pressure at the bottom of the pool and atmospheric pressure. Does that make sense? Because the idea is that, like, if you think about what's going on inside the person's head, so let's say this is the person's ear canal right here, and let's say this is their ear, right? The idea is that the pressure inside of here is at atmospheric pressure, okay? And when we're at the bottom of the pool, the pressure down here is going to be something like, we'll call it P, right? We know it's more than atmospheric pressure, right? In fact, we kind of know that it's going to be about how much pressure? If you're 5 meters deep, after we just did the example a second ago, what do we think the pressure is going to be at 5 meters? 1.5 atmospheres. That's exactly right. That's very good. You guys figured that out really fast. That's good. So we know the pressure is higher because atmospheric pressure is 1 atmosphere, right? So that means that with the pressure inside your ear being P naught and the pressure on the outside being P, then it's the difference between these two that you will feel, right? Because you don't feel any pressure on your ear right now, do you? Does anyone? Anyone feel any pressure on their ear right now? Maybe some of you do. I don't know, but most likely you probably don't, right? However, if you were to get in your car and go drive up to the top of a mountain, you'd probably feel some pressure, right? You'd probably feel a change, right? Or if you get in a pool and you go to the bottom of the pool, you'd feel a change. Well, that's because your ear is very, very sensitive to pressure changes. Very sensitive to pressure changes. That's why you mostly feel these things in your ear. You don't feel it everywhere. You feel it mostly in your ear. Okay, so see if you all can figure this out. We want to calculate the force on the ear, okay? We want to calculate what is now going to be the force on the ear. Can you all give that a shot? If I give you like a few minutes here to try it out? Take some time to try to solve it yourself, and then we'll solve it together. Oh, and I don't know if you saw this part, but we're going to take the area of the ear, to be 1 times 10 to the negative 4 meters squared. There's a notification here. Where is it? Okay, and this time, by the way, hold off on putting your answers in the chat until I say so, okay? That way everyone has a chance to solve it, because often when someone sees what the answer is, it will distract them and make them think they're doing something wrong, and they'll make them second guess themselves. So don't put an answer until I ask for it, okay? You all, of course, are welcome to ask questions while we're doing this. So if you do have a question, feel free to ask or type it. either one, Robert, you're still going to get about the same answer. Either one that you want to use. I think it's usually okay to just use 1 times 10 to the negative 10 to the 5. When you're doing your homework, maybe you'd want to do the exact value, you know what I mean? But when we're doing this stuff, it's... Yeah, they'll be off. They'll be just a little bit different. That's right. Okay, is that enough time? Well, I just do it this way. Go ahead and put an answer in the chat if you got an answer. And if you didn't get one yet, that's totally okay. That's a lot. I think there may be... Those numbers, I think, sound right. So I think what happened with those first few answers is maybe one of the exponents you used was the wrong power. Was negative. It should have been positive or something like that. Yeah, I think 15 newtons sounds about right. Let's go and do the calculation real quick, and then we're going to take a break. So, of course, part of what you need to do here is you need to figure out what this pressure is right here. Now, I don't know what the best way to do this is, but I'm going to go ahead and start with what they say right here and show you, kind of work backwards almost. It says, you know, the air in the middle ear is normally atmospheric pressure. Therefore, to find the net force on the eardrum, we have to consider the difference between the total pressure at the bottom of the pool and atmospheric pressure. That means that there is a force on the outside of the ear, but there's also a force on the inside of the ear, and we need to find the net difference between the two, right? The way we would do that then is we would take the force coming from the... Really, we're finding net force here, to be more clear. And let's put it... I'll try to make this as clear as I possibly can. Okay, so force outside ear. Outside ear. This is going to be... P times A, right? And then the force inside the ear is going to be P naught times A. And the way it's going to work out is basically that you're going to have P times A on this side, and then you're going to have a smaller force that's going to be P naught times A on this side of the ear. Let's say this is the ear. Every time I try to write something small, it always comes out really bad. So if this is the ear, the force on the top is PA, the force on the bottom is P naught times A. So that means that the net force, right, is going to be equal to the difference between the two. So PA minus P naught A, which is going to be equal to P minus P naught times A. Does this part make sense to everyone? Okay. But we also know from this equation that P minus P naught is equal to rho GH. So we can plug rho GH in here for this and get that the net force is equal to rho GHA, or 1,000 kg per meter cubed, times G, which is 9.8, times H was 5 meters, times A, the area of the ear, was 1 times 10 to the negative 4. This might be where people, if you used positive 4 here, you probably would have gotten a much bigger answer. That means the net force acting on the ear is what all those things multiply together to be. Notice we didn't even have to put in atmospheric pressure. Did you all notice that? It's just not even there. So, anyway. And I guess you get about 14.9 when you do this. I'm just going to trust that you all are right on that one. That is what I remember the answer being. And this is like 10 times 1,000. What is that? 10,000. Wait a minute. How do you get 14.9? Now I have to do it myself. I got 4.9. Oh, I know why you guys got 14.9. I know why you got 14.9. That's going to be what this is equal to, isn't it? This is 14.9, isn't it? I bet. And I bet this is 10 newtons. So that the answer is 4.9 newtons. I think that's what's going on. Is that how you all got 14.9? Is you found the pressure, and then you just, Oh my god, what did I write down here? This isn't the right equation. It's force equals pressure times area. Sorry about that. My bad. So sorry to mistake you. I had that written wrong right there. Okay, so 4.9. Do you all agree with this answer? Okay, and if you got 14.9, do you see why that's just the pressure from the outside and you have to subtract the pressure from the inside? I want to make sure that that's actually what that number gives you. Let's see. Yeah. Yeah, that's exactly what happens. So in this case, it's the difference. That's the key thing in this case, that you have to find the difference between the two pressures to find the total force. Okay, so that's a decent variation of pressure with depth problem. We only have until 12:50 today. We're still going to take a break, though. I need to give you all breaks. So we're going to take a break till 12:15. So I'm going to stop the recording, and we'll come back, and we'll finish talking about these other